Hello and welcome to part 2 of Dev Maths and Stats Refresher course, Lecture 9. Now we look at some other distributions that are related to the normal distribution, almost built upon the normal distribution. And for this you're going to need this spreadsheet, 3distributions.xls, and we're going to generate some random variables that are normally distributed. I can call those x0 to x4. Then I'm going to make another random variable by adding up the other random variables and see what distribution that has. So we need to go off to this spreadsheet. So please do have a look and try and follow this if you have the spreadsheet. So here we got x0 and x1. So we got to generate some random, some instances of this random variable. And x0, I would like to have this mean. So I've decided that it's going to be 25 and the standard deviation will be 10. And then to see what we're going to do here, these are the actual values. So this is the first one. And what we're using is this function, which is fundamental to doing any kind of Monte Carlo simulation work in Excel, rand, which generates a number between 0 and 1. So every time you recalculate the sheet. So if you do anything else, it'll recalculate. If you enter something, it recalculates. Or you can press the button F9, press this button on your computer and it recalculates as many times as you want. See, this one's recalculating as well. So this number will always be between 0 and 1, but it's uniformly distributed. So you're equally likely to get any number between 0 and 1. It's a uniform distribution. So we need to use that to turn it into a normal distribution, which is what this does. So let's just get rid of this. This generates the number between 0 and 1. This looks it up, and this tells us this is the mean, this is the standard deviation from here and here, and the output from this function is the z-score. So essentially what you're doing is you're randomly generating a number in this table inside here and then looking up the z-score in reverse. And because most of the scores are in this red area here, because there's more, you're randomly looking up an area here and then looking backwards to find this one. Because most of the area is in this zone, most of the time you're going to get scores around 0 and 1. So it turns it from the uniform number into a score where you're much more likely to get scores around this area, much less likely to get scores in this area, and it gives you a normal distribution. So that's how this is working, but we're not going to test you on that. That's just the detail of how it's working for background. So what we're going to do then is take this, copy it, and just copy it down to here. Doesn't want to do. The numbers you see there are just a count of how many we have, so hopefully we'll have 1,000. So now we have 1,000 variables with this normal distribution, a mean of 25 and a standard deviation of 10. So every time you press F9, you'll get a new. What we've got here is using what the first part of the lecture was showing you, that if we choose any boundary, and I've chosen 37 more or less randomly, it's slightly above 25, what we can do here is predict. So this is where we're getting away from descriptive statistics to inferential. You're predicting what's going to happen with random variables. So it's predicting that out of this 1,000 here, it's using the normal distribution. So it's looking up the 37. So it looks up 37, that's what the blue one does, in a normal distribution with this mean and this standard deviation. So that's what these two do. This means 1 means the total up to that point. It tells it it's cumulative. So it's looking up as though it's just exactly as though we're looking up in the normal tables. So what we're doing is it's looking up the number here, giving you this percentage. And then because I want to know what percentage is above that, I'm doing 1 minus. So it gives me the proportion above that. And then I multiply that proportion by 1,000. and that's my prediction of how many will be above this threshold. Now, so this only depends on the theoretical way the distribution is set up and the boundary one. It's taking no information from this, so it's pure prediction of what's going to happen in the future with random variables. And then to check how it goes, this one here counts how many actually do turn out to be above 37. And so here I predicted 115, that stays the same because that's my theoretical prediction. In this case it was 126 actually above. If I keep pressing F9 I can see how well it does, so 122, so too many, so it's never all that was almost exactly there. So you can see the theoretical prediction is never exact, but it's well, almost never exact, but it's not bad. And one question for you during the year is how close can you expect your predictions to be to what pans out in reality? Okay, let's get on with the rest of the demonstration, which is that this one here, this random variable has mean 25, standard deviation 10. We often actually, and many tests rely on this random variable where the mean is 0 and the standard deviation is 1. If I just copy this and put it here, then because of the way I've copied the formula, it's now going to use this, so it's going to generate a random variable that works with those parameters. Let's just see if we can fill it in. Let's see. That's very exciting. Copy the blank cell. Yeah, so you can see these numbers are here very different. The mean is 0, the standard deviation is 1. So they're varying in the range of 0 to 1, 0 to 2, 0 to negative 2. This one here, with a mean of 0, standard deviation of 1, is known as the standard normal distribution. So it's going to have the same shape as this, but it's got this standardized level of 0 and standard deviation of 1. Now, what I'm going to do with the boundary here is this boundary of 37 is 12 above the mean. So from here to here is 12. In terms of standard deviations, that's 12 divided by 10 is 1.2. So it's 1.2 standard deviations above the mean. Therefore, the z-score is 1.2. So what I'm going to do here is take, again, 1.2 standard deviations above the mean. And because the mean is 0, standard deviation is 1. It just comes out as exactly that, 1.2. I'm going to use that for my prediction using the same formula here. And again, it gives the same prediction because it's based on the same formula, the same z-score. Then again, we'll count what we actually get in practice, and it'll be round about the same. Okay, so you can see it's again, you get the same kind of level of accuracy. It's roughly right. Okay. Right, now we can speed this up still further because I want a few more of these. Oh, I think I want that many. Yes, x0 to x4, and I want all of these to have the same. Let's hope it doesn't add 1 or anything. Good. And also have the same properties. So I want all this to be the same, and all this to be the same. So you see it's getting a bit faster now because we've set 1 up. So I want those to be the same. So now we've got x1 to x4 are all standard normal distributions. The variables have a standard normal distribution. This is I have to correct this. It's because of the way that Excel copies. Sometimes it decides to increase when you copy across. I want these all to be the same. That's better. You can see that all the predictions are 115.1, and every time you recalculate it, some are above, some are low. So we're trying to predict how many are going to be above this threshold in every case. Great. So those are all normal distributions. Hopefully we've got to here. Oops, I need to expand that a bit. Okay. So the next thing I'm going to do is I'm going to make a new distribution, and what I'm going to do, instead of generating it like these are all generated, I'm going to make this distribution dependent on these. So it's going to equal to the sum of these three. No, of these, yes, 2, 3, 4. Yeah. So this variable here, this random variable, is equal to the sum of x2, x3, x4. So these are being generated randomly, and then whatever they add up to is equal to this. So I'm just going to repeat that all the way down. So it's a random variable, and it's equal to the sum of 3 normally distributed random variables. The question is, what kind of distribution would this have? What would it look like? Now, if it was still a normal distribution, then according to the theory that we did in class in the lecture yesterday, the mean, the expected value of this, should be the expected value of this plus this plus this should just be the expected value of all 3 things added together. So this should be just this here. The standard deviation, remember, from this is not just this plus this plus this, because remember the variance would be equal to this squared plus this squared plus this squared. Well, because they're independent. So variance of a plus b plus c is equal to the variance of this plus the variance of this plus the variance of this minus the covariance. But because they are all independent, all the covariances between these will be 0 because they're being generated independently, 2, 3, and 4. But that's the standard deviation. The variances added together, so the variance would be 3. The standard deviation would be the square root of 3. So I predict that this would be the square root of 3, 0.73. Therefore, if I want to have the same kind of boundary, about the same number above it, my boundary is going to have to be set as the mean plus 1.2 lots of this. So here I'm going to do 1.2 standard deviations times this. So that gives me 1.2 standard deviations above the mean. If it's still normal, I should be able to predict using that. And then I can count how many we actually get. And you can see again, it's not bad. It's pretty close. Okay. And now, in fact, it does turn out if we put it on a chart, and you can prove this theoretically, that when you add some normal distributions, in fact, you could get this. This is the distribution of I think x2. So it's a standard normal distribution. So this is what I mean by the standard. So the mean is 0, and almost all the numbers are within 2 standard deviations of the mean. Very rarely you get one above that, and it's got this normal distribution shape. Then this is what I get with x5 when I've added up 3 other normal distributions. You see, what's happened is that the mean is still 0, expected value is still 0 because it's this plus this plus this, but there's slightly more spread now because the variance is equal to the sum of the variance of the others. The standard deviation is the square root of that sum, so it's square root of 3. So it's just coming a bit wider, but you're still having a normal shape. Because it's still normal, that means we can still predict successfully using this normal function or normal tables. Still use that, do that prediction. Okay, so much for that. The next thing I'll do, which I'll do in the next video, is to generate another normal variable, which is going to be, well, 2 more normal variables actually. The variable 6 is going to be the square of the square of this standard normal variable. So instead of adding them, I'm going to square a normal variable. And here I'm going to do something more complicated. I'm going to square several normal variables and add those together and see what kind of distribution we get. But I'm going to save that for the next video. So for now, thank you for watching.